तुम्हारे लिए बोल रहा हूँ
क्या
विश Hello students, I welcome you all to the lecture on the topic Analytical Methods and Finite Difference Method. In this lecture, we will discuss the various analytical methods with example of course, and then we will proceed to solve these examples with the help of finite difference method. Nature is full of phenomena, and all these phenomena are governed by a set of coupled nonlinear partial differential equations which are a function of time. For example, when a batsman hits a ball, the distance covered by the ball depends upon the velocity of the ball and the angular trajectory. It also depends upon air velocity and drag, but neglecting these factors gives us a simple set of equations which can easily be solved manually. These differential equations are simplified by taking assumptions and are solved for exact solutions using various techniques available in literature. But to obtain this solution to a realistic model, we take help of numerical methods. Well, the thing is that while deriving the governing equations is not difficult, after all they simply are the summation of force or energy balance equations. Well, solving these differential equations for a set of boundary conditions poses quite a challenge. In the next few slides, we will see various systems of interest and solve their governing equations analytically to obtain the exact solutions to the problems. We will be taking the following examples. From strength of materials, the axial deformation of bar and the bending of beam. From heat transfer, the heat transfer problem from a fin is going to be considered, and from fluid dynamics, we are going to solve the thin film lubrication problem commonly represented by the Reynolds equation. All these examples are going to be simple, therefore they are going to be one-dimensional, linear and steady in nature. By one-dimensional I mean that they are going to involve only one space coordinate commonly represented by x. They are going to be linear in this sense that the material property are not going to depend upon the unknown parameter for which the solution is being sought, and by steady state I mean that the solution is not going to depend upon the function time. The axial deformation of a bar is governed by where U is the axial deformation of the bar, E is the elasticity of the bar material, A happens to represent the cross-section area of the bar, and Kx represents the loading on the bar, which in this case happens to be the volume load At this point, we will define a standard which is going to be used in this presentation. On the display, there is a equation underlined by a solid red line. In fact, the equation is also in red in color. This particular style of writing is going to be used to repeat the equations which have been derived in the previous slides. This is just for the reference purpose, so that equations derived previously, most commonly in the previous slide, are going to be referred in the next slide. Now, in this equation, that is the equation for the deformation of a bar, the elasticity, cross-section area, and the loading can be function of x. That means that they can vary as at different places. They can have different values at different places. But the thing is that these values cannot be a function of the deformation itself, because this is going to make these particular equations nonlinear, and this is one thing which we are going to deal in the future classes. But for the time being, it is just assumed that elasticity, cross-section area, and Ex are they can be function of space only. The problem can be more complex when the elasticity of the material is a function of temperature, it is strain dependent, it is strain rate dependent, and the load is a function of time and some other factors also. All these factors and many more of them are going to make the problem nonlinear in nature. Among all these variations, the simplest is a bar which has been loaded, which has a constant UDL, and the bar has a constant cross-section area, and it has a constant elasticity. That is, the bar is made up of one single material. And for this assumed problem, we can use analytical methods to get the exact solution of the problem. In fact, the analytical methods are going to be so simple that we can solve this particular problem even manually. We do not require any calculator or computer to obtain its solution. So we start with the simplest case possible. We assume that there is a bar of a constant cross-section area throughout the length. It is loaded by a UDL that is represented in red in this particular figure. UDL is a uniformly distributed load, and since we are analyzing the case of a bar, this UDL is going to produce only axial deformations of the bar. Kindly remember, if the direction of the UDL was oriented towards the perpendicular direction, this element under loading would have bent in that particular case. So this would have been a beam and not a bar. But for the time being, the direction of UDL is along the length of the element. So therefore, the element is going to act as a bar and not as a beam. Other thing is that the bar is simply supported at the two ends. We have a positive x direction from the left to the right, and if the length of the bar is represented by capital L, the left end is going to be at x is equal to 0, and the right end is going to be at x is equal to L. The governing equation has already been discussed earlier, given by equation on the display, in which the symbols have a meaning which have already been discussed earlier. Since this governing equation is second order differential equation. It is second order because the unknown u is being differentiated twice. Since this particular equation is second order differential equation, it is going to require some boundary conditions to obtain its solution. The standard rule is, since in this equation u is being differentiated twice, that is it is a second order differential equation, all the boundary conditions which are going to be used, which are going to be required for its solution, are going to be one order less than the differential appearing in the differential equation. Now, since this is a second order differential equation, the boundary conditions are going to be in terms of u or du by dx, or any combination of these two. In this case, we are using the known value of deformation at the two ends. Kindly note that we are not using, prescribing any given value of a slope, that is du by dx, at the two ends. We are using the value of deformation itself. Since the bar is constrained at the left and at the right, the value of deformation at the two ends is going to be 0 itself. For constant elasticity and cross-section area, the differential equation gets simplified to, and when we integrate it twice, we get an equation containing a term x square. In fact, there is a term containing x also, and we have two unknowns, c and d, which can be solved for the two boundary conditions which were on display in the previous slide. Using the boundary conditions, at x is equal to 0, u is equal to 0, which gives the unknown parameter d to be 0, and for x is equal to L, u is equal to 0. Therefore, c is equal to kx al by 2, which gives the equation as the solution. It can also be noticed that this is a quadratic equation, since there is a term containing x square. Now, using different values of input parameters such as e, a, kx, we can obtain the solution at different values of x to get the value of displacement on that value of x, and we can very well have a graphical plot. Since x is a continuous parameter, it can have any value. It can have literally any value. That means it can have infinite number of values. Therefore, this particular equation has infinite degrees of freedom. For e is equal to a, e is equal to 1, a is equal to 1, and L is equal to 1, the exact solution is plotted on the graph. Kindly notice that this particular plot happens to be symmetrical along the central axis, and the deformation is 0 at the two ends, that is x is equal to 0 and x is equal to 1. These were the boundary conditions which we have chosen. In this graph, the length of the bar is along the x-axis, and the axial deflection of the bar happens to be on the y-axis. The deformation in this particular case is axial deformation. It is not vertical deformation, because we are solving this particular problem assuming that it is a bar and not a beam. The next example which we take is from a beam. It is a simply supported beam on display. The beam has a length L. It is represented by 2 points A and B. It is acted upon by load W, which is not exactly at the center but is somewhat shifted towards the left. It is acting at point C. The differential equation is on display now. In this equation, Y is the deflection, E is the elasticity, I is the moment of area moment of inertia, and M happens to be the moment itself. Kindly note that M is M, which appears on the right hand side of the differential equation, is not directly available from the information given in the figure in the problem. In the problem, we know only the value of the load acting on the beam. So this load has to be converted. It has to be multiplied by distance from a reference point before it can be converted to moment, and then the value of moment is going to be used in this governing equation. And second thing is that the value of moment is going to vary. It is not going to be constant throughout the beam. And next is the boundary conditions. The boundary conditions have been prescribed at the two ends of the beam. That is, since the beam happens to be supported at the two ends, the value of deformation at both the ends happens to be 0. Now coming to the solution steps. First of all, we are going to find the reactions at the 2 points A and B. And since the load is acting at a point C, we are going to obtain the moments for the two sections of the beam, that is section AC and section BC. For the section AC, we are going to find an expression for the moment, which is going to be different for the section BC. What I want to say is both the section AC and BC are going to have different expressions for the value of moment. For AC, if we assume a section at a distance x from the support at point A, the moment at this particular location is simply going to be reaction at point A multiplied by that distance x. And if we take a section on the right hand side of point C, then the value of moment is going to be reaction at A multiplied by x, that is going to be subtracted by load W, and is going to be multiplied by x minus A. So this is how moment is going to be acting. It is going to be found at the two sections of the beam, and then these two moments are going to be substituted in the governing equations to have a number of unknowns when the differential equation is going to be integrated twice. The unknowns obviously are going to be found using the boundary conditions and some other conditions which are going to appear on its own. The additional boundary conditions which are going to appear on its own are going to be the value of deflection and slope at point C on the beam. For both the sections AC and BC, the value of deflection at point C and the value of slope at point C is obviously going to be the same, and this is going to be used to find the value of additional unknowns which are going to appear in the solution. Now coming to the solution itself, We first of all find the reactions RA and RB. First, starting with section AC, the bending moment is given by the reaction at point A multiplied by X, where X is the location from support A, of course. Substituting the reaction, the moment in the governing equation, and integrating it twice gives equation number 1 after the boundary condition has been substituted in it. Kindly notice that C still is one of the unknowns which is yet to be determined. Coming to the next section, that is section BC. The bending moment is and integrating this twice gives equation number 2, having two unknowns E and F. Now one of these two unknowns can be found by using the boundary condition that y is equal to 0 at x is equal to L, and the other boundary condition, other unknown, is still going to remain in the expression. Y is equal to 0 at x is equal to L, and the second set of boundary condition which we are going to use is that the slope at point C is same for both these sections. This gives us the final expression for deformation to be equation number 3 on display. And kindly notice that this particular expression happens to be a cubic expression because there is a term containing x raised to power 3. There is going to be a quadratic term, that is x raised to power 2, also in the expression once we expand the second term on the right of the equality sign. And this can be the solution to this equation can be obtained by assuming different values of W, E, I and L, and can be plotted in a graph. For these values assumed, the graphical solution is going to be, the solution in the graphical plot is going to be given by this thing. Also notice that in this case the deformation happens, the deflection, not the deformation, the deflection, the lateral deflection of the beam happens to be symmetrical with respect to the central axis, and the value of deflection is 0 at the two ends. The next example which we take is from is a heat transfer problem from a fin. Fin obviously is some projections which are protruding out of a hot surface and are to be used to cool the temperature of any body. Most common examples of fin which we can find around us are fins in the case of an IC engine, that is in a motorcycle or a scooter. Those fins obviously are air cooled, and the governing equation which is going to be used in this particular case is going to be equation on the display. Kindly note that this expression has a value Q on the right which represents the internal heat generation, and it also includes heat loss because of conduction, but there are no convective losses to the atmosphere. In fact, fin by themselves have no internal heat generated in itself, but simply to this equation is simply going to be used to represent the possible type of heat interactions existing in the system. Obviously, convection has not been included so far, because then we have a second order differential equation. This similar equation to what was being used earlier in the cases of a bar and in case of a beam. In this expression, K happens to be the thermal conductivity of the material, A happens to be the cross-section area, Q is the internal heat generation, and there are going to be a set of conditions used for this also, which is the value of temperature, known value of temperature at the two ends, that is at x is equal to 0 and x is equal to L. We are assuming that the temperature is 0 at both the ends. This is being assumed because then we are using basically the same sort of boundary conditions which were using in the earlier examples. And using the similar steps, we can find the distribution of temperature. Same expression was obtained for the case of a bar also, and we get the same expression for the case of fin over here. And this can be plotted for the assumed value of K, A, and Q. Which again is symmetrical with respect to the central axis. The next example, in fact the last example which we are going to take, is from a fluid mechanics problem. It is a thin film lubrication problem. The governing equation for this particular case is represented by the popular Reynolds equation as on display, where H is the fluid film thickness, mu is the viscosity, U is the sliding velocity of the surface, and P is the pressure. In the next slide, we will describe the working of the lubricating system itself. So we have two surfaces represented in black. The upper surface is fixed, while the lower surface is moving towards the right with a linear velocity u. And in the red is the fluid, a viscous fluid. Every fluid has some viscosity associated with it. So that particular fluid is represented in red. And kindly notice that the two surfaces are converging when we move from the left towards the right. By converging, I mean that the gap between the two surfaces is decreasing as we move along the direction of the sliding velocity. Now, since fluid has a viscosity, as the lower surface is going to move towards the right, the fluid is going to have a tendency, because of its viscosity, of course, it is going to have a tendency of being pulled in the converging gap, because of which pressure is going to develop. This pressure can be integrated over the surface area to have a equivalent value of load, and this load is going to support the external load acting on the system itself. So this is how the fluid film lubricated bearing is going to work. And the governing equation obviously was displayed earlier. The boundary conditions are in terms of pressure. We have the known value of pressure at the two ends, because the two ends of the bearing are exposed to the atmospheric pressure. So we can assume that the ambient pressure is 0 at the two ends, that is at x is equal to L and at x is equal to 0. Now the solution to this particular problem is going to be obtained using the similar steps as illustrated earlier, but these steps are not going to be illustrated over here. They have been left as an exercise to the students themselves. Now in this particular slide we are going to compare all the differential equations which we have studied so far. We have the differential equation for a bar. We have a differential equation for the beam. In fact, in beam there is one more differential equation which is commonly in use. The first differential equation for the beam is the relationship between the moment and deflection, while the second differential equation on display is again a second order differential equation. In fact, it is a relationship between moment and the load acting on the beam. And then we have a differential equation for heat, and at the end we have a differential equation for the fluids. Now kindly notice that all these differential equations appear to be similar. They are similar in fact, which means that if you are able to make a program for one of the problems, assuming that you are able to make a finite difference program for a bar element, for a bar problem, then simply by making some substitutions you can solve the problem for other cases also. If you compare the differential equation for a bar with respect to a differential equation for heat, you can notice that in bar we have E and A, while in heat we have K and A. Similarly, on the right hand side we have Kx into A, while for the heat we have Q. So this means that if you replace elasticity by thermal conductivity of a bar, you can very well convert the program made for bar with respect to the program for heat. So what I want to say is, by simple substitution of one parameter to another, you can convert one working program to solve the range of phenomena which are following the same differential equation, same second order differential equations. Now continuing with the comparison, all differential equations are second order equations. They are steady state also, because we have intentionally omitted the term time from the equations. They are one dimension because they had only x as the space coordinate. In fact, in engineering, all differential equations which find practical applications, obviously in engineering we study only practical cases. So in engineering we have differential equations which are second, fourth and sixth order only. Second order differential equations we have studied in the previous slides. Fourth order differential equation is going to be studied when we study the case of deformation. Sixth order differential equation finds application for adhesives, and differential equations which are first, third or fifth order, that means odd number of differential equations, odd ordered number differential equation, they exist only in mathematics but do not find any application from the engineering point of view. Only the mathematicians study first, third, fifth, seventh and so on. But as far as engineering is concerned, we have only second, third and sixth order in differential equations. As far as my information goes, we do not have a 8th order differential equation also. 8th and 10th, we don't have differential equations of these higher order differential equations. Now coming to some observations regarding analytical solutions. analytical methods gives a closed form solution, that is, they gives us a exact solution to the problem. They give the value of the unknown at any point specified by x. Thus, they have infinite degrees of freedom, while the numerical methods, they give solution to only some predefined points. Therefore, they have finite degrees of freedom. The predefined points can obviously be increased in number, but still they are going to give you the solution at only the locations which are going to be defined before the solution process actually starts. And they are obviously, these points obviously are going to be countable. They are going to be finite in numbers. Therefore, these numerical methods always have a finite degrees of freedom. They do not have infinite degrees of freedom. Despite the fact that various numerical methods are popularly in use, analytical methods are always going to be around. There are always going to be plenty of persons, there are always going to be plenty of mathematicians which are going to work to find the exact solution to a given problem. Now, in the remaining slides, in the slides which are going to be on display, we are going to discuss some fundamentals of finite difference method, and then we are going to apply the FDM process to the problems which we have discussed using analytical methods in the previous slides. The finite difference method was among the first approaches applied to numerical solution of differential equations. It was first utilized by Euler, probably in 1768. The finite difference method is directly applied to the differential form of the governing equation. Kindly notice that the finite difference method is directly applied to the differential form of the governing equation. It does not alter the differential equations in any form as is commonly done in some other numerical techniques, but it uses the exact form of the differential equations which are going to be the governing equations. The principle is to employ a Taylor series expansion for the discretization of the derivatives of the flow variables. Flow variables are the unknowns which are appearing in the differential equations. They might be in terms of velocity, pressure, temperature, deformation, and things like that. The finite difference method, or FDM as they are commonly known, are discretization used for solving differential equations by approximating them with differences equations. The differentials appearing in the governing equations are approximated by the differences equations. FDM converts linear ordinary differential equations or nonlinear partial differential equations to a system of equations that can be solved by matrix algebra techniques. The reduction of the differential equation to a system of algebraic equations make the problem of finding the solution to a given ODE, PDE ideally suited to modern computers. Hence, numerical techniques like FDM find widespread use. Other numerical techniques which are in common use happen to be finite element method or FEM, boundary element method or BEM, and some meshless numerical methods are also fast being developed to be applied in some complex cases. Today, FEM are the dominant approach to numerical solutions of PDE. This is primarily due to simple theory in FDM compared to other numerical methods such as FEM, BEM, and some other numerical meshless methods. The Taylor series polynomial is given by the following expression. The idea is that if we know the solution at a given point, that is represented by x0 over here, we can use the Taylor series expansion to find the value of the function at a point x0 plus h using the equation on display. Kindly notice that in this particular expression, terms such as f1, f2, f3 are the first order, second order, and the third order differential of the solution. That is, f1 means df by dx, f2 means d square f by dx square, and so on. Also notice that there is a last term on the right given by Rn. This happens to be the residual, or it is also known as the error, and depends upon the number of terms which have been taken in the Taylor series expansion. Now this Rn is a crucial factor in the this Rn is going to play a crucial factor in the solution obtained by FDM, depending upon the number of terms which you are going to take in the Taylor series expansion. The Rn is going to be very small, or it could be negligible, or it may affect the solution to a significant extent. This we are going to see in the coming slides. In the following slides, we will obtain approximations to various derivatives by truncating the Taylor series. We are starting with the first derivatives of the function f, given by expression on the display. First derivatives, when we are approximating, we are getting the approximation for the first derivative. We keep only the first derivative in the expression and neglect all the higher order terms. Therefore, all those terms which have been neglected are going to be represented by the last term on the right, that is R1x. R1 because only the first order term has been included, and this R1 is a function of x because at different points in the domain, that is at different x in the domain, the residual is going to vary. The residual is not a constant thing throughout the domain, but is going to vary along with the position. Now when we are interested in finding the first derivative of the function, this is the expression from where we start, and we are simply going to rearrange the term so that f1x is on the left hand side and the rest of the term are on the right, such as over here, and then the h, that is the difference between x naught and the point where we are interested in, that h is going to be transferred from the left to the right. In fact, it is going to appear in the denominator, such as is displayed over here. So the last term, that is the residual term, in fact is going to be divided by h also. So the error in this particular first order differential is not r1x, but it is r1x divided by h. Assuming that r1x is sufficiently small, the approximation of the first derivative of f is given by the expression on display now. So kindly notice that this particular approximation is applicable only under the condition where r1 is sufficiently small, or you can say that r1 represents the error which can be neglected with respect to the other terms appearing in the equation. Now we are going to see in future slides that r1 is itself going to be approximated by several terms. This formula is also known as the forward approximation of the first derivative. Coming to the backward approximation of the first derivative, we simply replace h by minus h in the Taylor series expansion, such as, and then we are going to neglect some of the terms as we have done previously. And then in the next step, we are simply going to neglect r1, that is under the assumption that the residual r1 is negligible, and then we are going to rearrange the polynomial, the equation on the display. Now this is the backward difference. Now there in fact is another difference known as the central difference approximation of the first order, and this we are going to derive in the next slide. So for obtaining the central approximation of the first derivative, we take two Taylor series expansions, such as kindly notice that in the first expression we have positive h, which has been replaced by minus h in the second expression, and then we simply manipulate these two expressions, such as and taking the difference of these two equations, we get the required formula. Now in this expression, that is the last expression, we have a term represented by O within bracket h square. If you simply compare equation number 3 with the previous expression on display, you can very well find, you can very well conclude, or you can very well know the expression for the order of error, that is OH square. In fact, it is going to be F3 divided by 3 polynomial H square. So this is the error when you are representing the first order polynomial with respect to the central difference. In fact, the order of the error can be found in a similar method for the backward and the forward also. Backward and the forward approximations also. And you can very well find that the order of approximation, order of the error in approximation is of the order of H. And since in this particular case the order of error in the approximation H is H square, therefore from the computational point of view, the central difference method happens to be much better compared to the forward and the backward approximation. But as we will see in the further slides, from the application point of view, the central difference method has certain constraints which are not applicable to the forward and the backward method. Some other first order approximations are, so apart from the approximation, you should also have a look on the error in the order of approximation. In the first equation on display, the order of the error is H square. That means that as you go on reducing H, that is the 2 point in the discretization, as they're going to approach towards each other, the error in the approximation is going to reduce as a function of H square. Similarly, we have another approximation. And the third approximation, the order of the error happens to be H cube. But then if you compare the third equation with the first or the second equation, you can very well see that in the first and the second equations there are only 3 terms. Talking in terms of the first expression, for finding the first order approximation using the first approximation, you need to find the value of f at 3 points given by x plus h, and x plus twice h. There should have been twice h. And similarly, from the second equation, for finding the first order approximation, you need to find the value only at 3 locations given by x plus h, and x plus twice h. But in the third equation, for finding the first order differential, you need to find the value of the function at 4 points. Therefore, the computational work increases, but I suppose that is going to be compensated with the reduced error in the solution which you are going to get. Similarly, we have a fourth expression also, which is on display now. And the fifth expression, which requires the function to be evaluated at 4 points, has the order of error in the approximation given by h raised to power 4. So depending upon the accuracy with which you want your solutions to be obtained, you can use any of these formulas on display apart from the 3 which we have derived earlier, given by the commonly used forward, backward, and the central approximation. Similar to as we have developed the first order differential equation, approximation to the first order differential, we have a number of expressions for the second order also. We are going to develop the second order central difference in this slide. For this, we start with two Taylor series expansions given as, this is the first one and this happens to be the second ones. The only difference between these two is that one is a step forward, therefore it is written with plus h, and the other is a step backward, therefore it is written with negative h. Now these two expressions are going to be manipulated in a particular order, which is going to be shown in the coming slide. The first step is to drop a number of terms. We are retaining only the fourth order derivative in this expression. So all the terms which have derivatives higher than the fourth have been dropped in these two expressions. And then we add these two expressions to get the final expression on display. And then we are going to simply keep the second order differential on the left and rest of the terms on the right. Which gives us the 3-point formula to be evaluated at x naught plus h, x naught minus h, and x naught. And there is another term which is the last term on the right, which is the fourth order differential. That is going to be the error in approximation. So this is the final approximation. Kindly notice that the order of error in this approximation is h square. The second order forward difference is given by this expression. The backward approximation is this. And the forward approximation with respect to x naught. The other two terms are being calculated at x naught plus h and x naught plus twice h, therefore it's a forward. In the backward approximation with respect to at a location x naught, the other two terms are at x naught minus h and x naught minus twice h, therefore it's a backward difference. There is a third approximation also, which in fact is a second difference, central approximation, because with respect to x there are two terms which are evaluated at x plus h and x plus twice h, and there are two other terms which are evaluated at x minus h and x minus twice h. So this is a central approximation for the second order. Now in the following slides, we will solve some problems with the help of finite difference methods. We will solve the same problems as we have solved previously using the analytical approach, but in this particular case, we are going to illustrate the solution to the previous problems using finite difference method. Now finite FDM solution for a bar. So we have a bar, simply supported bar, and there happens to be a uniformly distributed load acting on the surface of the bar. The governing equation, we have already discussed that, and the boundary conditions are that at the two ends given by x is equal to 0 and x is equal to L, the deformation at both these points is 0 because the ends happen to be constrained. Now for obtaining the finite difference, the solution through finite difference method, the first point is that the domain is to be divided into a number of parts. The domain is the area in which the solution is being sought. So in this particular case, the bar itself has to be a domain, and since we are looking for a one-dimensional solution, the domain is going to be represented by a line. And in the present solution, because the solution is going to be obtained by FDM, finite difference method, but still the equations are going to be obtained manually. So we are dividing the domain into 4 parts. All those parts happen to be of equal size, and they are going to have 5 nodes. So this is the first part indicated in black, second, third, and the fourth. And kindly notice that in FDM, the standard procedure for obtaining the solution through FDM requires that the domain has to be divided into parts of equal size. Therefore, the 4 parts which have been used over here, all these 4 parts happen to be of equal size. But supposing if this was a 2-dimensional domain, that is a rectangle, let's say, or a square, let's say, then the length along the x, length of the divisions along the x and along the y, they need not be same. So we have the first node at x is equal to 0. U obviously represents the deformation. So since we are talking about the first node, the unknown is going to be represented by U1, that is deformation at the first node. And since this particular node is constrained, the value of deformation is going to be a known quantity, that is 0. Now this is the second node located at x is equal to 1 by 4, and that is going to have the deformation is U2, which is unknown. Over here is the fourth node at 3 by 4. Here it is the third node at x is equal to 2 by 4. And at the end there is a fifth node, x is equal to x is equal to 1, and the deformation is known over here. Therefore U5 is equal to 0. All the divisions happen to be same. Therefore the 5 nodes are located at equal distances. That is at x is equal to 0, then x is equal to 1 by 4, x is equal to 2 by 4, x is equal to 3 by 4, and x is equal to 1. So since we have 5 nodes, out of which deformation is known at 2 locations, that is at the first node and at the fifth node, therefore this particular discretization is going to give us requires only 3 unknown values, that is U2, U3 and U4. So for obtaining 3 unknowns, we are going to require 3 equations, and we are going to see that these 3 equations are going to be coupled linear simultaneous equations, which are going to be solved using the Gauss elimination method, which you have studied in your BTech classes. So for the time being, we are going to use the central difference for the second order differential. Central difference for the second order differential. This is the governing equation, and for constant values of elasticity and cross-section area, this can be simplified to take E and A outside. Kindly remember that in this particular case, Kx represents the load per unit volume. It is not the load per unit length, it is the load per unit volume. Obviously, when Kx is multiplied by A, it is going to give you load per unit length. That is A and A gets cancelled out, so E we are taking on the other side. Boundary conditions are obviously known to you. So we are going to replace the second order differential, that is d2u by dx square, by the difference equation. For simplified calculations, we are assuming that all parameters have a value 1. Same thing was done for the analytical approach also. So equation now becomes, the governing equation now becomes d2u by dx square is equal to -1, and the second order difference is on the display. So when you apply the second order differential, the second order difference to the second node, x0 becomes u2, then x0 plus h, that gives you u3, and x0 minus h gives you u1. So when you apply the having u3, u4 and u2 as the unknowns. Similarly for the fourth node, now equation number 1, equation number 2 and equation number 3. In this equation, u1 and u5 have a known value, that is 0, but as you can see that the three equations have three unknowns in the form of u2, u3 and u4. These three equations form a set of linear simultaneous equations and are going to be solved to get the three unknown values of u2, u3 and u4. Now in this equation, all the equations, 5 equations have been written together. In fact, equation number 1 and equation number 5 are the two constrained equation, and equation number 2, 3 and 4 are the three equations which have been obtained by applying the difference equation at the node number 2, number 3 and number 4. Now these 5 equations can be written in a matrix form . Can be solved for the 3 unknowns. Now there are some observations regarding the matrix which we have obtained for the 5 equation. First observation is that there are plenty of zeros in the matrix. That means that the matrix is sparse. Next observation is that there are non-zero terms in the three central diagonals. In fact, some specialized algorithms have been made to obtain the solution to the simultaneous equations in which the three central diagonals happen to have non-zero quantities. This particular algorithm is known as TDMA, Tri-Diagonal Matrix Algorithm, TDMA. So the algorithms are popularly known as TDMA algorithms. Now the other observation is, since the matrix happens to be a sparse matrix, various algorithms have been made to take the advantage of this scarcity. This we have already discussed in the previous slide. These equations obviously can be solved using the conventional Gauss elimination method, but we are going to see in the future slides that the conventional approach of solving the linear simultaneous equations using Gauss elimination method is not a very efficient method of solving the equations. For solving the simultaneous equations in MATLAB, we are going to use a command known as INV. The name of the command itself is INV because MATLAB has all the built-in routines which possibly you are going to use. MATLAB is the software, popular software, and the name of the software itself happens to be Matrix Laboratory, in short MATLAB. It is going to contain all the routines regarding matrix operation which we can possibly think of, and therefore it is finding popular applications, popular acceptance among the students and research scholars. This is one software which you should learn, really seriously learn, if you want to do some computational work. In the next few slides, we will solve the bar problem as discussed earlier. The solution is going to be obtained both via exact method that we have already done and the numerical method, that is through FDM. The FDM solution is going to be obtained for 5, 6, 7 and 10 nodes. Kindly notice that this FDM solution has already been obtained for 5 nodes. We have obtained 5 equations for 5 noded discretization. Out of these 5 equations, 2 were the constraint equation and the remaining 3 were obtained when the difference approximation was applied at the remaining 3 nodes. So that gives you 5 equations. So we have already derived the 5 equations, that is the solution using 5 nodes. We have not obtained the solution, but we have derived the equations. Now similar steps are going to be applied to obtain the solution for 6, 7 and 10 nodes, and it is going to be seen that how the solution varies as the number of nodes are going to be increased in the discretization. and then these solutions are going to be compared among themselves. Please notice that the accuracy of the numerical solution as the number of nodes are increased. This is the exact solution. In fact, the exact solution has been obtained using the plot has been obtained using the exact polynomial which we have derived earlier. So this is a smooth curve. We are using the same boundary conditions for all the solutions so that we can compare these solutions among themselves. Now this is the solution when we discretize the domain in 5 nodes. The exact solution and the approximate solution, that is the solution we get through FDM, they are same at the nodal locations. But apart from the nodal locations, obviously, as you can see, that the solution given by FDM and the exact solution, they have some error. Now this error is going to decrease, or you can say the solution is going to, the accuracy of the solution is going to increase as you go on obtaining the approximate solution using higher number of nodes. It should be noticed that exact value of displacement is found at the nodes. The maximum error is located at the center of each node. You take 2 adjacent nodes, and at a location which is in between these 2 nodes, that is the location where these solutions, where the 2 solutions are different to the maximum extent possible. So the error is maximum between the 2 nodes. This is the solution for 6 nodes. For 7 nodes. And for 10 nodes. So it can be seen that when you are working with 10 nodes, the exact analysis and the FDM solution, that happens to be almost identical. You can very well go on increasing the number of nodes to have a better approximation. In the next lecture, we will develop the program for the finite difference method using various approximations for the derivatives. This program will be in MATLAB environment.